The following is part 2 of a sequence of videos dealing with moments and center of mass. This video deals with the calculus portion, while the previous video dealt more with the algebraic version. Now before we go any further, let's talk about the symmetry principle, which states that if a region R is symmetric about a line I, then the centroid of R, or also known as the center of mass or center of gravity, lies on that line I. Now you could go even further. Let's say if you had a circle, for instance, then the center of mass would be obviously at the center of the circle. Let's deal with the center mass of a lamina. Now a lamina is a thin plate. Let's first find the center mass of a lamina, which is defined as the region below a curve f of x, above the x-axis, and between the lines x equals to a and x equals to b. And let's let rho be the density of the lamina, where rho is defined in terms of mass per unit area, such as grams per square meter. Then first, for the mass of the lamina, let's consider the following rectangle, which we have in red in this picture. Let xi star be the midpoint of the interval forming the rectangle, where delta x is the width of the interval. The area of the rectangle is defined by the value of f at xi star times delta x, again the width of the interval or the rectangle. So the mass of the rectangle is rho times that f of xi star times delta x. Now the sum of the masses of the rectangle approximates the mass of the lamina, so the mass of the lamina is approximately the sum of the rho times f of xi star times delta x, where I goes from 1 to n. Then these are Riemann sums, and if we take the limit as n goes to infinity, then the mass of the lamina is equal to the limit as n goes to infinity of that sum from 1 to n of rho times f of xi star times delta x, which is equal to the integral from a to b of rho times f of x dx. Now that we have the formula to calculate the mass of the lamina, let's look at the moment of the lamina with respect to the y-axis. Now the moment of the rectangle is the same as the moment of the centroid of the rectangle. That's going to be very important for us, so that when we're calculating the moment of this rectangle, we could just do it in terms of the center of that rectangle, and using the symmetry principle, the center of that rectangle would be, the x-coordinate would be that xi star, which remember was the midpoint of that interval, and the height of that would be the value of the function at that x sub I star divided by 2. So the moment of the rectangle with respect to the y-axis is rho times f of xi star times delta x times xi star, because remember it's the mass times the distance from the y-axis. The moment of the lamina with respect to the y-axis is approximately equal to that sum from 1 to n of that rho times xi star times f of xi star times delta x, which again will give us a Riemann sum. So the moment of the lamina with respect to the y-axis would take the limit of that sum as n goes to infinity, which would be the same thing as rho times the integral from a to b of x f of x dx. We could pull out that rho because rho will be a constant. Now the moment of the lamina with respect to the x-axis, well, for one thing, to find this, that the distance from the center of the rectangle to the x-axis is that, again, the f of xi star divided by 2. So the moment of the rectangle with respect to the y-axis, remember, is the mass times the distance to the x-axis, which would be the rho times f of xi star times delta x times f of xi star divided by 2. Now the moment of the lamina with respect to the x-axis is approximately would be the sum of the rectangles, which would be the sum from 1 to n of 1/2, because I could pull out that 1/2 to the front, 1/2 rho times f of xi star squared, because we have an f of xi star times another f of xi star times delta x. So again, looking at that as a Riemann sum, and as the n goes to infinity, that the moment of the lamina with respect to the x-axis is equal to rho times the integral from a to b of f of x, that quantity squared, divided by 2 dx. And I just realized in that previous formula we were using m sub y when it should have been m sub x. Now for the definition of putting that all together, let R be the region bounded above by the curve f of x and below by the x-axis between x equals to a and x equals to b. Let rho be the density of the lamina. The mass of the lamina again is given by rho times the integral from a to b of f of x dx. The moments m sub x and m sub y of the lamina with respect to the x and y axis are given by m sub x is equal to the rho times the integral from a to b of f of x squared divided by 2 dx, and m sub y is equal to rho times the integral from a to b of x times f of x dx. And using that, we can find the center of the mass of the lamina, which is at the point x bar, y bar, which is given by that x bar would be taking that m sub y divided by m, so take the moment with respect to y divided by the mass, and the y bar will be equal to the moment with respect to x, the x-axis, divided by the mass. Now we could take that even further by looking at a lamina bounded by two functions. Let's say if it's bounded above by f of x and below by g of x. Then let R be that region bounded above again by the curve f of x and below by the curve g of x between x equals to a and x equals to b. And let's let rho be the density of the lamina. The mass of the lamina is given by m equals to rho times the integral from a to b of f of x minus g of x dx. The moments m sub x and m sub y of the lamina with respect to the x and y axis are given by that m sub x equals to rho times the integral from a to b of the f of x squared minus g of x squared divided by 2 dx, and m sub y is equal to rho times the integral from a to b of x times the quantity f of x minus g of x dx. And the center of the mass is at the point x bar y bar, which is again given by that x bar is the moment with respect to the y-axis divided by m, and y bar is the moment with respect to the x-axis divided by m. So let's finish this off with an example where, let's say, we have a semicircular region bounded by the y-axis and the graphs of f and g, where f is the square root of 9 minus x squared and g of x is the negative square root of 9 minus x squared, where x is between 0 and r. So again, it's a semicircle centered at the origin, and it's the right side of the circle. And we're to find the moments and center of mass of, or center of gravity, same thing, of this region R. So a little small, but using the formula for the area of a semicircle, which is a equals to 1/2 pi r squared, we know that the mass is equal to 1/2 rho times pi times r squared. Because remember, the mass would be the density times the area of the region. We could use the formula, the integral formula, to find the area, or we could just use, again, that we know the area of a semicircle. Now the moment with respect to the x-axis, that m sub x is equal to rho times the integral from 0 to r of 1/2 of the f of x, which is the r squared minus x squared, that function squared, minus g of x squared, which is r squared minus x squared, and then dx. So that ends up giving us 1/2 times rho times the integral from 0 to r of 0 dx, which is just 0. And that makes sense if you think about it, that at the moment with respect to the x-axis, since it is symmetric about the x-axis, that the moment would be 0. The moment with respect to the y-axis is equal to rho times the integral from 0 to r of x times the square root of r squared minus x squared minus negative square root of r squared minus x squared dx. Let's simplify by combining those two radicals and pulling out the constant, so that would be equal to 2 times rho times the integral from 0 to r of x times the square root of r squared minus x squared dx. Now to solve that integral, we could do a basic substitution. Let u equal to what's underneath the radical, the r squared minus x squared. du would be the negative 2x dx. And when we do that, we'd end up with negative 2/3 rho times r squared minus x squared, that quantity to the 3/2 from 0 to r, which would equal to 2/3 rho r cubed. So using the formula, we can now find the center of the mass, which is equal to x bar. The x-coordinate of the center mass would be 2/3 rho r cubed divided by 1/2 rho r pi r squared, which would equal to 4r over 3 pi. One thing to note, for both the x bar and the y bar, the rows would always cancel. So again, the x-coordinate of the center mass is at 4r over 3 pi, where again r is the radius, and y bar is equal to 0 divided by 1/2 rho pi r squared, which would be 0, which again makes sense because, as we said, by the symmetry of that semicircle, that it is, the centroid is on the x-axis. So the center mass is at the point 4r over 3 pi comma 0.